Okay, good morning, students. Today is June 28th, and we are completing chapter 3. It is a short chapter. We're going to explain how to use minimum potential energy in order to solve some in a not exactly the precise way. It's an approximation. It's what we call the scheme, which is very simple. And at the end, some of these ideas, you will see that we can use them in the future, okay? But it's still, it's very simple way to apply these ideas of energy, okay? And at the end, I will present how to calculate, for example, critical load for buckling, right? In the past, we used to use this application in order to deduce an expression for the critical stress, not of beams or columns, but of plates, okay? So it's a nice application, but we cannot reach that far because we have not yet employed or applied plate theory. So yeah, that will be just a way that you can see how can we use these things, okay? Okay, and at the end, we're gonna have some minutes in order to talk about exams and things like that, which are, we have to make some change because of the present situation of the country. Okay, so that's the agenda for today. Isaac, can you see my screen? Full screen?
Yes.
Isaac? Okay. So this was the last part of the last class, right? Here we have the idea behind this method, okay? It's basically, we are saying is that if we apply a load, in this case on a beam, okay? Because of this load, the beam deforms. And because of this deformation, the force is displaced, okay, moves. And once force, one load is displaced, he or she develops work, okay? So this energy has to go somewhere, right? And this energy goes inside the system, the structure, right? And in our case, we absorb this energy as a partial as energy in pure bending and partial energy in shear, right? So what we did in the last session was we deduced this expression, okay, as the strain energy because of pure bending. For this, in this specific case, this is a statically determinate case, we deduced an expression for the bending moment inside the beam. And with this expression, we integrated and we obtained this expression, okay? Then we deduce an expression for the shear force, replace it in the expression for the shear stress, integrated that all along the beam, and we obtain this expression here. So now this work has been transformed into this internal energy. And from here, we can get the displacement of the beam, of the end point of the beam. Okay, this is a nice example, but there is another message here, is that we were able to express this result in this way, okay? And maybe you can recognize that this term multiplied by 1, the first part, corresponds from the internal energy from bending. That means that if we use pure bending to analyze this beam, this is going to be the deflection of the end point, okay? But now, since we are considering the effect of the shear, this is the influence from the shear, okay? And the thing is that this term could be of a magnitude which is completely neglectable or could be of some importance. And this difference is mainly driven by this ratio, H over L, right? So if the height of the beam divided by the length of the beam is small, then all of this term is very small and neglectable, right? If it is not the case, then this term is of importance compared to this one. That means that if this is the case, then this term is of importance compared to this one, and we have to include it if we want to estimate the final deflection of the beam. And more or less, this is what we did, and we said that that's the common rule, right? If H over L is less than 1 over 10, this term here will be smaller than 1.01, basically. So that means that if we neglect this is going to be less than 0.01. That's 1% of that. Okay, so if H over L is less than 1 over 10, this is going to be less than 1% of that. And that means that basically we can neglect it. Okay. In the case of the ship, okay, that's not completely the case, right? So this could be, for example, 1 over 9 or something like that, or right in the edge, 1 over 10. So that means that in general, in the case of the ship, we should think about considering this, the influence from the shear in the deflection or in the stress distribution, okay? So more or less, that's the general idea of that. We're going to continue now. Okay, so basically this is conservation of energy, okay? Now, the method in the way we have presented can be explained only, or can be applied only in cases where we can deduce expressions for the shear force and bending moment. And those are statically determinate cases, okay? So let me put here the date. Today is June 20. Okay, with this, I'm going to close this part. This process of calculation the deflection can be applied statically determinate beams or structures, right? If you want to calculate the deflection using this method, we could do it, but we have to get a little bit more and we have to deduce another method, which is based on this conservation of energy. But we are not going to do that, okay? We're going to present something a little bit different in the following. But what we have done, be careful, can be applied to statically determinate beams only, okay? So let's put here, if you want to calculate delta for indeterminate cases, you have to by other energy methods. Simple methods to do it, but we don't have the time to present them here, okay? So that's it for that. Let's go on now with another topic, okay? And this topic is the principle of minimum potential energy, okay? Minimum potential energy. So this principle states this, okay? If you have, if you want to find a stable equilibrium, okay, then the potential energy is a minimum, okay? We have to be careful because in some cases, for example, it's typical, right? You have two situations like this one, okay? In this case, for example, you have a ball at the top of a hill and you have a ball at the bottom of the throw. If you move a little bit this, you're going to find, okay, an equilibrium which is well outside the original, way away from the original position. If you do something like this, okay, it will oscillate until finally you come back. Okay, so this is what we call an unstable equilibrium, and this is an unstable equilibrium. Both are static equilibrium, okay? But if we're looking for an unstable equilibrium, that's this case. In this case, the potential energy has to be a minimum, okay? Remember from your differential calculus, right? If you want to find an extremum, what you do is you differentiate, right? And you make this derivative equal to 0. That allows you to find the maximum or the extreme, okay? Now, if you want to find the minimum or maximum, that depends on what? Do you remember how to differentiate the maximum or minimum? Anybody remembers? Okay. So if you have df over dx equal to 0, you find an extreme, right? But in this case, you have a maximum or minimum. How do you remember how to differentiate from maximum or minimum? Anybody can remember? Differential calculus?
With the second derivative.
Exactly, with the sign of the second derivative. So we have to be careful with that, okay? So what we have to do is we are going to present the definition of the potential energy, which is this one here, okay? So the potential energy is the combination of the internal and strain energy. Okay, this is strain energy. Okay. And this is the potential work of the external forces. Okay, this is the potential work of external forces. Okay, now if we are able to calculate or approximate, this is the way we're going to do it. If we can approximate the potential energy, we're going to call it PE. This is the pi letter, a capital. We're going to differentiate, right? But the problem is that when we apply these concepts in calculus, okay, we have one single variable, right? But in our case, okay, the shape that the beam takes when you apply a load, okay, the shape could be different, right? So what we have to do in general is that we should try to find several mathematical forms for the deflection and try to see which one causes the minimum potential energy. So it's going to be a much larger procedure. Okay, so let's try to write it here. In general, the deflection function, that's V of x, okay, will influence potential energy. So we should try to find the one which uses minimum. Okay, so it's like a much wider procedure, right? Because it's not just a fact that you try to find an x value to have the minimum or maximum. In this case, it's like trying to find a function, V of x, which makes P, the potential energy, minimum. Okay, so, but don't worry. See, this idea you can apply in order to, you can imagine that this is like a philosophical statement, and we can apply these things in many different ways. Okay, we're going to use it in a very simple way, and that's what we call the Rayleigh-Ritz procedure, which will be presented in a few minutes. Okay, now, or in the case of this class, okay, I'm sorry about this, I wrote on the title, we're going to use it to analyze beams, right? So in the case of beams, okay, we have pure bending, okay? And in case of pure bending, we have this, this is an expression to calculate the strain energy, okay? So you remember that this is basically 1/2 the integral over the whole volume of sigma x squared over E dV, right? And then you start recalling that sigma x is equal to minus mz times y over the inertia. And you go on and finally reach this expression here, okay? So please put this in your memory, okay? You can either start from here and finally reach this expression, or you can simply try to recall this expression, okay? So please get a paper, write it 2, 3, 4 times until finally you can recall it, okay? Because you can see that this term, the bending moment, is squared. I sub c, it's always in the denominator. So it's easy to get confused, okay? So please try to remember, okay? Something which is very, very interesting is that this term, okay, in the numerator has a square. That means the numerator is always positive, right? The denominator, Young modulus, and the inertia are always positive. That means that if you integrate this, this is always going to be positive. Okay? So you take a beam, you push it upward, and because of the deformation, it stores energy. The same beam, instead of pushing upward, you push it downwards, right? So it deforms. And again, the strain energy is going to be positive because the beam stores energy inside its mass, okay? So be careful with that, okay? If you integrate this and obtain a negative value, then you are in trouble because that's incorrect, okay? So these are little things that should help us, right, in order to check our results, right? Because in some cases, you can get a large integration and you can make mistakes, right? But if you at the end get a negative value, don't see it. There's something wrong there, okay? That's it. The other term is remember, this is not the work, it's the potential work of the external loads, right? So if you have a beam, okay, you have a beam like this, right? And you have a force, this is force per unit length, right? So you take a dx here, right? So you multiply this times that, and you can consider, since dx is very small, the force on this little element is equal to this df is equal to p dx. Now, since you apply this force, it has the potential to be displaced. How much? V of x. So this is the force, okay? And this is the probable displacement that this force can take, okay? So remember, this is not work, this is the potential work. And in this case, you recognize there is no 1/2 in front of this expression, okay? Now, here comes the problem, okay? As we said before, in this case, if we choose a V of x, okay, a V of x, with this V of x, we can differentiate twice and calculate the bending moment. With this bending moment, we can put it into here and calculate the strain energy of the beam, right? This V of x, we can put it here and we can integrate the lateral load. So we can add these two. And we have, right now, in that point, we would have one value of the potential energy, okay? Then you can imagine another type of force, of function, right? For example, in one case, you could take a polynomial, quadratic polynomial, right? You can evaluate U beam, you can evaluate the potential energy of the lateral load. But now you can take another form. For example, you can take a sinusoidal, sine pi x over L, right? And you can, again, differentiate twice, multiply by EI, that's the bending moment, put it into the expression for the U, and you have it, a value. You can also put the deflection here. You can integrate and have a potential work of this load. And you have a different value of pi, right? So it's a tremendous work, right? Because we have to try so many type of functions, right? So one way that we can apply this process in order to find approximations, one more time, approximations of the solution of bending is the Rayleigh-Ritz procedure, okay? Rayleigh-Ritz method, okay? So, as I said before, it's a very complex situation, right? Because you can imagine many forms for the solution. So how can we differentiate? Well, there are some ways to do it, okay? Some people call it variational calculus. We're not going to go into that. So what we can do is something much more simplified, and this is what we call the Rayleigh-Ritz method, okay? How we do it? This is the way we do it. Okay, you can see here immediately that this little sign is like a little wave, because this is not the exact solution. This is just an approximation, okay? So let me insist on that. So this is, we propose an approximation. A solution, okay? So let's make a difference here, okay? Every time we see in this subchapter V star, okay, that's the precise solution. We're going to find V with little wave, meaning that this is just an approximation, okay? So please, how we do it? We simply specify that as a group of parameters. There are many ways that people call this parameter, and we're going to call it just the amplitudes, okay? But in the literature, there are many ways that they can be called. And this is like the proposed function. Now, this function have to satisfy the geometric boundary conditions, okay? So this is very important, okay? So each one of these FIs have to satisfy the geometric boundary conditions. That means that if you have we should make a quick difference here, okay? I'm going to change color just in case. Okay, so I'm going to make an explanation here, okay? Remember that the equation that we're trying to solve is this: EI sub C, V comma 1, 2, 3, and 4 is equal to P of X, okay? So you see that we have fourth order of the differentiation, right? So the boundary conditions, okay, could be values of V of the first, second, or third derivatives, right? Now, if you specify values of V comma X, this is what we call geometric boundary conditions. These are geometric boundary conditions. And values of second or third derivative are what we call natural boundary conditions, okay? So when you apply Rayleigh-Ritz, right, you have to propose functions, and these functions have to satisfy the geometric boundary conditions, okay? For example, if you have a clamped end, Mr. Cedeño, Axel Cedeño, if you have a clamped end, okay? What are the boundary conditions in the case of a clamped end, Mr. Cedeño, Axel Cedeño?
Deflection on the first slope is 0.
R0, yes.
R0.
So in this case, you're saying value of V and value of the first derivative. So both are geometric boundary conditions, okay? So you have to choose a function which satisfies these two boundary conditions, okay? What happens in the simply supported case, Mr. Guaman? In the simply supported case, what are the boundary conditions for the support? Mr. Guaman? Mr. Guaman, please. Mr. Guaman, are we having problems with the connection? Can we talk? Can you talk? Turn on your microphone, Mr. Guaman. Mr. Tenemea, in the case of a simply supported, in the simple support, what are the boundary conditions?
The the deflection and the bending moment is 0, doctor.
Are 0, yes. And can you say something about the type of boundary conditions? If you say that the deflection is 0, that's a geometric or natural?
The geometrical, I think
it's a geometric because it's a value of V, right? And you can see here, we are saying that when you have a value of V, that's a value of the geometric boundary condition. So V1 is a geometric boundary condition. How about the other one? You said that, what was the other condition, Mr. Tenemea?
is the bending moment.
Okay, and the bending moment is a natural or geometric boundary condition?
Is the natural.
Yes. Why you say that?
That's because the reactions
How do you express the bending moment in terms of V? How do you express the bending moment in terms of V? Ms. Jimenez, how do you express the bending moment in terms of V?
The first moment,
No. The bending moment. How do you express the bending moment as function of V, the deflection? Chapter 1. No? Don't recall? Mis Puertas. Mis Puertas, can you hear me?
yes, teacher.
How do you express the bending moment as function of V? How do you express the bending moment as function of V?
The
bending moment, I'm going to write it here. Bending moment here. So you have the bending moment. Can you express that as function of V? No? Mr. Llanos, can you help us? Mr. Llanos?
Good morning, doctor.
Hello.
The bending moment is equal to Young modulus times the inertia and times the second derivative of the
Exactly. Exactly. So you have something like that. Okay, so if you say that the bending moment is 0, Young modulus is never 0. One more time. Young modulus is never 0. And the inertia is never 0 because that's the integral of y squared, right? So you can have any value, but every time you square it, you get it positive. So you either have a section, immediately you have inertia. You have a material, you have Young modulus. So you cannot have EI sub C. You always have different than 0. So if you want the bending moment to be equal to 0, the only possibility is that the second derivative is equal to 0. Okay, so going back to the questions to Mr. Tenemea, in the case of the simple support, we have two boundary conditions. One is the value of the displacement, that is a geometric boundary condition. And the other is the bending moment, that's a natural boundary condition. Okay? Let's go to a better one, a nice one. How about the guided? Do you remember the guided case? The guided case, Mr. Kimi, Elvis Kimi. Do you remember the boundary conditions for the guided case, Mr. Kimi, Elvis Kimi?
No, Doc.
No?
No.
Miss Poveda? Miss Poveda? Good morning, Miss Poveda. Poveda, you're not here? Miss Poveda? No, she's not here, Isaac.
Okay.
Miss Valdez,
Yes, doctor. The shear force is equal to 0 and the first derivative of the deflection is 0.
Okay, so would you say that those boundary conditions are natural or geometric?
One
That's
is
a good-
natural and the other is geometric.
Geometric, yes. Which one is natural?
The third derivative of the deflection.
Exactly, exactly. So these are little details. Well, not little details. This is something that we have studied. Yeah, shear force is equal to minus EI sub C V comma 1, 2, 3. So if you know the shear force, the value of the shear force, you can specify the value of the third derivative, right? Because usually you know the Young modulus and you know the inertia, yes. And the other is geometric, yes. The slope, which is the first derivative, is equal to 0, okay? Finally, in the case of the free end, that's a nice case, right? Mr. Hidrobo, do you remember the boundary conditions in the case of the free end?
The shear force is 0 and
Shear force is 0 and I didn't
in
hear
the
it.
end, in the free end,
Yes. Shear force is 0 and the other?
and the other is the moment is also 0.
Exactly. Are they natural or geometric boundary conditions?
Natural.
Yes, both are natural boundary conditions. Okay, so in each case, okay, we have to identify which one of these boundary conditions are geometric, okay? And we have to propose functions that satisfy these geometric boundary conditions, okay? Now, let's assume that we can propose a function, okay, that satisfy the geometric boundary condition. What do we do next? Okay, so in this case, in this expression that we have proposed here, so f of I is something that we know completely. So we have to determine is what's the value of a sub n. Okay, so these are, it's like having a changing variable. Right now, the variables are a sub n. Okay, and since you try to find the minimum, what we can do is we can differentiate, okay, partially of the expression for the potential energy with respect to each one of these amplitudes, okay? So from here, we're gonna have a set or a system of n, I'm sorry, it's large n. We're going to have system of n algebraic equations to find the a sub n's. Okay, and n goes from 1 until n. Okay, in this course, okay, we could try to find, for example, a group of 2 of this function. I'm going to do an example with 1, but we can do for 2, okay? So that's the process, okay? So first, we have to identify, in your case, what are the conditions that we have to satisfy, and those are the geometric boundary conditions. Then we have to replace in the expression for the P, integrate, get the potential energy, and then once we have a full expression for potential energy, you go on and try to get the minimum, okay? And what we have done is we have left these amplitudes as the variable. So it's like switching the values of a sub the different a's, right? So we assuming this function that we have proposed, we will get the minimum, in certain way, right? If by chance we propose the exact solution for Fi, in that case, we're going to get the exact value of the solution. If we get just an approximation, that's what we're going to be doing in the next example. We're going to get just approximations, okay? But it's much simpler than solving the whole thing, and you will see that, okay? So let's do an example, okay? This is a very simple example that you have in your class notes, okay? So we're going to have this, this case. It's a simply supported beam, okay, with uniform load over the whole length, okay, pointing downwards, okay. So that's easy. So here you have simple support. So we recall this. So we have the value of V and the value of the second derivative as 0. This something that we just recall. This is a geometric boundary condition, and this is a natural boundary condition. Okay, so we have to propose functions that satisfy this condition. Similarly, on the other case, okay, we have V equal to 0 and V comma XX equal to 0. This is geometric, and this is natural. Okay, so this is the condition that we have to satisfy. Okay, so we have to propose functions that are equal to 0 at X equal to 0 and at L equal to 0. Okay, so it reads, we have to propose functions which are equal to 0 at X equal to 0 and X equal to L. Okay, in your class notes, there's something like this. Okay, so this is there. And you can see that if you evaluate this function at 0, this is 0. So if you evaluate this, you're going to have something that which value 0 here, and this is this boundary condition. And the other end here, you evaluate this at X equal to L, and this is again going to be 0. So we satisfy both boundary conditions, geometric boundary conditions, okay? Now, I want you to tell me another boundary, another function. You have to propose something different, okay? Mr. Guaman, Gabriel Guaman, can you imagine another function which satisfies both boundary conditions? Mr. Guaman? Mr. Guaman, can you help me? And Mr. Guaman was having problems with the connection. Can you say something, Mr. Guaman? Because I see that you're trying to communicate. Anyway, let's go to somebody else because we don't want to wait. Mr. Soria, can you propose another function that satisfies both geometric boundary conditions? Mr. Soria?
Good morning, Doctor. Maybe X time L minus X to the square.
Yeah. Yeah, exactly. So that means that at 0 it's going to be 0, at L is going to be 0. So what we can do here is just to add, okay, and A2 multiplied by F2. And we can go on. Okay? We can go on. In this example that you have in the class notes, I'm going to consider only one function. I want you to include one more in the homework, which is coming. Okay? So we have this function, satisfy geometric boundary conditions. Let's go on. Now, once we have V, we can proceed and calculate the bending moment, the U. And then with this V, we can calculate the potential work, and then we can apply the minimum potential energy theorem. Okay, so here it is, the bending moment. You can see here it's approximated. See, we emphasize that it is just an approximation, and for that we use this function, and this is it. So we can differentiate twice this thing, and this is what we obtain. Okay, I'm sorry, you need calculus for this course. That's it. And now we can proceed to calculate U. So U is equal to mz squared divided by EI, 1/2. Okay, so I have EI v comma XX. Oh, so here we have the bending moment. This is the bending moment squared, and we can integrate this, right? And this is the result. Okay. Immediately we see something strange here, right? We have that this is negative. That means that this function, okay, we can use it, right? But so it's just an approximation, right? But let's put it here. Remember, this is an approximation. Okay. Okay, let's go on. Now we have U. We have to go now. The potential work. So potential work is equal to the integration of V P dx. Okay. So this is df. And this is just an approximation. That's it. So we can integrate both U and W to obtain those terms as function of the proposed functions to approximate the solution. This is just an approximation, remember. Just an approximation. And now, what's the minimum potential energy theorem says? That if we combine these two, okay, we should have the minimum. But the problem is that we don't know the function. We have done an approximation. Well, but what we can do is we can leave this parameter a sub 1, and what we're saying is that if the function were close to the solution, the best that we can do is take a value of A1 so that P would be minimum. That's what we're saying. We are not certain that this is the best solution, okay? And as a matter of fact, we obtain a value of U, the strain energy, which is negative, that gives us not a good feeling, right? Because we expect that amount to be positive. So in general, that's an approximation. And the best that we can do is select A1 so that this P using this approximated function is a minimum. That's what we are doing here. Okay, so we differentiate taking the parameter A1 as it were an independent variable, and we can get a value for A1, and that's the value for A1. So we can replace. Okay, so here we have all of this is A1, and this is the function that we call F1, which satisfies the geometric boundary conditions. From chapter 1, you can obtain the exact solution, okay? And the exact solution is this. Okay, this is the exact, that's why I'm using the star here. The star means that this is the exact. And you see that this is fourth order. Okay, I have x here multiplied by x cubed. So this is fourth order. And this is second order polynomial. So this is P sub dos of 2 of x. This is P of 4 of x. Of course, you can imagine that being P2 and P4, this is just an approximation. So what I did in the class note is I plotted both. Okay, I plotted in this way. I plotted here, it's EI sub C V of x divided by P0 L to the 4th. So this is a nonlinear solution. Dimensional solution, I'm sorry. And you see that it's a large difference. Okay, something that we could try to do would be to use another function and see if we can get the correct solution. But we want to find just approximations. You see immediately here that the geometric boundary conditions are satisfied, both start at 0 and end at 0. Those are geometric boundary conditions, but we didn't say anything about the bending moment, okay? So the bending moment, let's calculate the bending moment here. So it's going to be EI sub C, and we have to differentiate twice this thing, right? So we're going to get minus 2A1 times all of this. So it's going to be P0 to the 4th divided by 12 EI sub C. That divided by L. Yeah. So we cancel this, and we cancel this, something like that. And this is a constant. And the problem is that should be 0 here and here. So that's an error. It's not. that means that there is an error. Okay? Questions? People, is there any questions about it?
Yes, doctor. This is another method to find the deflection.
Just a second. Another method to approximate the solution.
Approximate. Oh, right. Yeah. Okay. Okay.
Yeah, the solution. Okay, approximate. Yes, we could apply it in many cases. Yeah. For example, let me open a new page here. Just a second, please. Can you see my screen, people? Can you see my screen? Full screen?
Yes, doctor.
Okay. For example, if I ask you to analyze this case. Okay, let's analyze this case. Okay. Okay, would you propose a function for this? Anybody? I want you to propose a function to approximate the solution of this problem. I insist this is not exact, this is an approximation. Can you do it? Yes, you can do it. Mr. Carranza, can you propose a solution for this?
Yes, doctor. A sinus P X over length.
Please repeat it again.
Deflection equal A sinus P X over length.
Okay, what are the boundary conditions that you have to satisfy?
In the X equals 0 in the complex, deflection equals 0.
And?
The first derivative equals 0.
The first derivative of this is equal to 0?
In the complex, yes.
If you differentiate this with respect to x, what do you obtain? What's the derivative of this with respect to x, Mr. Carranza?
Cosine.
Minus cosine. Come on, Mr. Carranza. Derivative of the sine is what? Mr. Romero, Jan Romero. The derivative of the sine is equal to?
Or ln menos cosine px over ln.
Yes. And the problem is that this function at 0, how much is this, Mr. Romero? Is this 0? At 0?
Is 1.
It's equal to 1.
So this is incorrect. And this is something that you should see geometrically, okay? If you draw the sign between 0 and L, this would be something like this. This is the sign. And then you continue like this. Here, the slope, you see it equal to 0, Mr. Carranza?
No,
No.
different.
It's different than 0. So this function does not help us. Okay, let's find something else. Let's find another proposal. Mr. Benavides, can you propose something to solve this, approximate this problem?
Good morning, doctor. We can try with x squared times L minus x.
Yeah, that would be. So it's going to be x squared L minus x. Yeah. Okay, in this case, this is value 0 here, value 0 at L, and differentiate this, and you can get again equal to. I think this satisfies. Okay. So the derivative to be divided by A1 is going to be equal to 2x L minus x plus x squared minus 1. So you evaluate this at 0, and that's going to be 0. So the first derivative is going to be 0. Now, again, the value at 0 is 0, the value at L is 0. So satisfy the 3 boundary conditions. Okay? And what would happen? What would happen in this case, for example? Let's suppose that we have something like this and like this. We can use this function to approximate it. How would we calculate the potential work in this case? Just think about it, okay? We're going to do a break, and when we return, we're going to answer that question. How can we calculate W in this case, okay? So